Thank you, Nika, for a great introduction. Hi, I'm Tom Esposito. I'm an astronomer. I hope you're all having a good day, that you've all gotten A's on all your exams today, all your posts have been liked, et cetera, et cetera. I'm really happy to have the opportunity to tell you a little bit about what an astronomer is, what it is that we do, how you make one, and some of the things that I've seen as an astronomer. Here we go. Okay, so we can start simple. Define astronomer. I've said it already about 5 times in 1 minute, so we should say what it is. I think you can explain it as a person who studies the branch of science that deals with objects beyond the Earth, space, and the universe as a whole. So the science of space essentially is astronomy. The people who study that are astronomers. None of this is astrology, which is totally different, and I won't talk about today. All right, but what does that actually mean, right? So we defined it, but what does an astronomer do? There's a few examples of what astronomer jobs could be. There's lots of different possibilities, but a few of them are, we can use the scientific method to learn new things about space, planets, galaxies, the Big Bang, asteroids, alien life, and so on. We call this doing research, okay? And we basically use the scientific method like you probably learned in your science courses. You form a question that you want to ask. You conduct observations to collect data. For us, it's usually from telescopes, where we can take images of things up on the sky. You analyze the data, you interpret, and then share the results and how they answer, or if they answer your question. But that's not the only way you can be an astronomer. You can also build or operate the telescopes, the cameras, the observatories that we use to collect new and better data. You'll hear about that more, I think, in the next talk. Or maybe you can create new models or theories of how our universe works. All right? So you spend more time thinking and imagining about how things could be in the universe. We call these people theorists, these types of astronomers. Or you can teach other people about astronomy or to do astronomy. And this is super important because if we don't pass on the knowledge that we've gained, the things that we've learned, then what good is it, right? If you can't pass that information on, then it's just lost. So what about this particular astronomer up here? Well, that's me. I'm Tom, again. That's me on top of a volcano in Italy from a recent vacation. I am a doctor, technically, because I did a PhD in astronomy, but I couldn't save anyone's life if I needed to. I'm from Long Island, born and raised, which is outside of New York City. Some of the things I like to do are anything at the beach, sun, sand, surf, you name it. I played soccer my whole life. That's how I did this. Big baseball fan, Yankees forever. Like to grow vegetables and plants, flowers, like to read, and play video games. Anyone could take me at Call of Duty, but I will beat anyone here at Mario Kart. Come at me. Education, so astronomers are scientists, right? So I had to go to school. That is just one of the way it works. I went to public school my whole life, so all the way through high school, public schools. I liked science. I thought I wanted to do physics because that was the science that I enjoyed the most. So when I went to college at Georgetown University, I did 4 years of getting a bachelor's of science degree in physics. We actually didn't have astronomy there, so I couldn't just study astronomy. Then I went to UCLA in Los Angeles to do my PhD. So when you finish college, if you want to do the type of astronomy research that I do, you typically need to get another degree, which is a PhD or a doctorate, and that takes about 5 or 6 years. So that's even more school, but that's where I really learned to do science. That's where I learned to be an astronomer and to do what I do. And then I've had jobs since then, luckily, or I probably wouldn't be here. And so some of those jobs are doing that research that I mentioned earlier where I'm just studying the universe. Essentially, I do that at UC Berkeley, and now at the SETI Institute, which is Berkeley's across the bay, but SETI is right next door in Mountain View. So that's an organization of astronomers that all work together in one group to do our research. And then I've recently worked with private companies like Unistellar and SkyMapper two that I'll mention briefly later, where we actually try and merge science with technology and the public, so people just like you, to do astronomy in a different way. Okay, so we've talked a little bit about how you can be an astronomer and sort of what that means, but I want to take a minute to, for you to think about what a professional astronomer actually does at work. So if you imagine me on a typical work day, what do you think I do? So just take 20 seconds to yourself and think about that. Okay. Hopefully you've all had a chance to think about one thing that I do. If I could get your attention back. So here's what I think you might have imagined that an astronomer does. One, we put on our pajamas and go up to the roof and look through old school telescopes. Two, we make pretty pictures, things you see on the internet. We draw constellations and figure out which animals we want to make next. We write a bunch of silly equations on a chalkboard and then think about it for a while. Or we go to space and we float around. You don't really float in space, but that's a different story. Some of these are, they're all reasonable. Some of them are more true than others. So what do we actually do? What do I do kind of on the daily, day to day? I do a lot of this. Most of modern astronomy is done on your computer. So I sit at a desk in an office most days. I write a lot of computer code. I read a lot of computer code. I run a lot of computer code. And this is so we can analyze and process and get results from the data that we've taken. So that is a lot of astronomy these days. But we do need the data, so we do need images of the sky. We need to use telescopes. So I will spend time, sometime every month, taking images with telescopes and mountaintops from around the world, or even from our backyards, which I'll mention later. We look at the images, so there's data that we get from the telescopes, and we process with our code. We actually have to look at them, and so sometimes I'm looking at pixel by pixel, what is actually in my image, what's real that I care about, what's noise that I don't care about, how do I interpret this? If I'm an observational astronomer, I'll do this often. If I'm a theorist, I will do this less often. But they will do other things. So what we don't do a lot of is make these pretty pictures. They're great to look at. They are super useful, and scientifically we can learn a lot from them. But typically the average astronomer doesn't spend a lot of time making these pretty things that you see. Those theorists that I mentioned actually will write down a lot of equations and then think about, they imagine, how does the universe work? What would it be like if this planet orbited this star in a different way? What if there were two planets? What if the planet had a moon? These are things that theorists will think about. Sometimes I will do math myself, but I try to avoid it whenever I can. Honestly, I don't love math. It's very important. You need to learn how to do it. You have to be able to do it as an astronomer. You don't actually have to enjoy it necessarily. That's an inside secret. We do meet and talk with other astronomers all the time, often on Zoom these days. We need to share ideas. One way we do that is by reading and writing scientific journal articles. So that, this is a way that we have like a standard format, basically, that we agree as scientists. All right, I'm going to tell you what I did, what question I was investigating, how I investigated it, what I found, and what I think about that. And then that's there for everyone in the world, basically, to see. And we basically never get to go to space. I wish that weren't the case. You can apply to be an astronaut if you're an astronomer. I've done it. They didn't call me back. But some astronomers, some astrophysicists actually do get to go to space and be astronauts. It's just that we can do a lot of our work from here on the ground, on Earth. And so oftentimes they'll send other types of scientists up into space to do their work. All right, so those are some of the things that we actually do as astronomers. So I want to take another 20 seconds. Just think about which qualities and skills you think that I need or an astronomer needs to do those jobs. So again, 20 seconds, and I'll come back. It's a short talk, so that's all the time you get. All right, so hopefully you've thought of one thing that I need to be able to do. I guess one of them is speak out loud. That's a gimme. I'm doing that now. So which qualities and skills do I think an astronomer needs? All right, we've already said you need to learn a bunch of math and physics. Yeah, it's kind of unavoidable. Astronomy is a mathematical science. You got to learn a bunch of it. Like I said, you don't have to be Einstein. You don't have to be a genius. I'm not. You don't have to actually love or be incredibly good at math. I do math every day. I don't enjoy hard math, but you do need to be able to do it. Computer coding, like I said, super important these days. If you can write your own code in some common programming languages, you can learn a lot more from your work and do it a lot more easily. But there's one thing that maybe, I don't know, a lot of people don't think about as a skill or a quality that astronomers need. And that's creativity. Right, so we are problem solvers. That's what science is solving problems. And most of the time, that problem has never been seen before. You don't know the answer in advance. So sometimes you have to be creative. You have to think about, all right, what if I have to think about this from a different perspective? Let's try and solve this problem in a different way. I'm going to do something that no one's ever done before. That's creativity. You have to be able to, or the best astronomers I know have this creativity. It's not just musicians and painters and dancers that are creative. Scientists are too. A few more, some qualities maybe, things that might mean that you could be an astronomer. Do you like taking pictures and staying up late? Be a telescope operator. Do you like solving puzzles? Be one of those theorists who spends their day thinking about, all right, how do I solve this problem? Do you like building things with your hands? Be an instrument builder. Be the person who puts together those lenses and mirrors and electronics and lasers to build the cameras and the telescopes we use to collect our data. You like sharing the knowledge that you've learned? Be an educator. Be a teacher. We need more teachers in everything. We really need teachers in science, people who care about doing it and passing on that information. It's super important. Like I said, if you don't teach it, then why have we learned it? Your teachers didn't pay me to say that. It's important though. You have to do a bunch of work on your own. You'll need to be able to say, okay, this is the question that I want to investigate. I need to motivate myself to do it. Here's how I'm going to go about it. But you also usually need to work in a team because astronomers, there's lots of different skills that are involved, things you need to know, a lot of work to be done, and doing it on your own would take a long time or maybe be impossible. You need to be able to work with other astronomers, partners who will help you. And then one more also that maybe doesn't come to mind very much. You have to think differently, all right? So if you think that you're different, if you feel like you don't fit in, that's okay, right? This is a good thing in science. We need to think about these problems in different ways. We need to not answer the questions that have been answered before. Why bother? We need to answer the questions that haven't been answered yet, and even better, we have to ask the questions that haven't been asked, all right? And the way we can do that is if you're thinking along different lines than the people who came before, the astronomers that have done this for millennia. And then persistence, just about like with anything, you have to try again. And the reason for that is science is hard. You will fail. I fail constantly, every day. You'll fail a lot. There are a lot of days, basically weekly, where I wake up or I'm in the middle of the day, I ask myself, why am I doing this to myself? Why did I choose this? I should have been a farmer. Not to take anything away from farmers, right? Super important work, very you got to know a lot to be a farmer. But sometimes it feels like I wish I could just go outside and plant some seeds and water them and pick the fruit. Because it's hard and it's frustrating. So why do we still do it? So I can tell you why one astronomer does it, or I can show you. Okay, so this picture here is a ring. It's a picture from a telescope of a ring of rocky and icy dust orbiting this star, HD 156623. Name doesn't matter. What matters is that I was the first human in the history of humans to ever see this and know that this existed. That's because when I got these data, I processed the data, I made this image on my computer screen. That was the first time that had ever been done. And to me, that is amazing and profound, and that's what keeps me doing this. I discovered something. And for a brief period, I was the only person who knew this. Not for long, because pretty soon I was like, hey guys, look at what I found. But to me, this is very cool. And I think it's one of the key things that makes science worthwhile. If you discover a rock that orbits the sun, and all you know is that how this rock goes around the sun, but you're the expert on it, like that's your rock. Right? That is your rock. And no one can take that away from you. And you've contributed something to our knowledge as humanity that doesn't go away. So for a little bit more context, because I know if you're not someone who does this all the time, looking at this picture doesn't really mean much. You can picture this so at the center here is a star, which in this artist's drawing, the star is in the center, this bright point, and there's this rings of dust, like a Frisbee or like a DVD, orbiting around the star. And the dust is there because there are large rocks and comets, asteroids, that are orbiting the star as well. And some of them are forming into planets, because this is a young solar system like ours. It's actually starting to form. But some of them actually collide and get ground up, and they make tiny little dust particles. And then those dust particles reflect the light from the star towards us here at Earth. And that's the bright orangey pink stuff here that we see. This is the starlight reflecting off of these tiny dust particles. So that's how we know these young solar systems are there. And this is, I'll get more into this, but this is good for us to know because it tells us there are other solar systems out there and ours is not alone. Okay, so discovery is an important part of being an astronomer. And now I'll show you some of the things that I've done quickly towards the end here before we wrap up for questions. What a real astronomer does with their time. So one of the things I've spent a lot of my time doing is studying exoplanets. So these are planets like Earth, Jupiter, Saturn, but in other solar systems, not our own. One of the ways we do that is by pointing large telescopes like this one or this one, which the mirrors here, the shiny bits, those are about roughly the width of this stage here. So they're big. And you need those big telescopes to gather the light from these exoplanets. And so you can see, for example, here's a movie of watching one of these planets, Beta Pictoris b, that goes back and forth. It's orbiting around its star. We watch it going from one side of the star over the course of about 17 years, I think, past the star where we lose it for a minute, and then we see it orbiting back around the other way. This is interesting. We've never, 20 years ago, we just started being able to do this. And it tells us something about how these Jupiter-like planets, these are big planets like our biggest in our solar system, Jupiter, how they orbit, what those solar systems are like. Can you have Earth-like planets there? How might it affect if those Earth-like planets can have life, et cetera? So here's another movie, similar thing. We're seeing a different planet, but this one we're looking top down from above. You can actually see the planet starting to do its orbit around the star. And we have to watch it for more than 4 years to see it go all the way around, but I was part of the team that helps discover this planet even exists. And then just a fun one, this is the first multi-planet system where we could do this. Actually, there's 1, 2, 3, 4 planets that we can watch going around the star. And then learn, again, how do you know, our solar system doesn't have 4 giant Jupiters like this. So this tells us that our solar system is not like all the others. You can also use those telescopes to make those pictures like I showed 2 slides ago, those rings of dust to see these young solar systems. This is something that I did a few years ago, and there's just lots of different variety, lots of different types of and shapes of solar systems you can have. And then the last thing I'll mention here today is besides doing that pure research that I just was showing, I've been partnering with companies like Unistellar, which makes these smart digital telescopes that have computers and cameras built in. Anyone can buy these. And we, as the scientists, as the astronomers, partner with the people who buy these telescopes around the world. There's 15,000 plus of them, these yellow dots. And some of them are nearby. This is Sophie and her dad, Fadi Saibi, who Sophie goes to high school right near here. They do science with us. And so these people with these telescopes, who we call them citizen scientists because they're not experts, they're not professionals, but they can still do astronomy because we show them how, and then we work with them to do it. They can make all of these observations over the course of a year. Each of these pink dots is one of their observations of supernovae, which I'll show in a second. But thousands of these observations to help us do astronomy. And what we're trying to do is combine science and technology to transform astronomy and take it from only the professionals who have the time and the access to get a PhD can do astronomy and do science, to anyone being able to participate. So I'll leave you with this. So this is a movie of a supernova. So it's something we study is these exploding stars that are dying. They're at the end of the life. They explode. We call them a supernova. They're in other galaxies outside the Milky Way. Most energetic events in the universe. We can see them in this galaxy here. This is one in the Pinwheel galaxy. You can see it's got these spiral arms like the Milky Way would have if we could look at it from outside. And this point of light, you'll see when the movie is looping, it starts out, it's not there at all. I'll go back actually. There's nothing here in this circle or in this box, which is zoomed in. There's no light there. And then when this star, this supernova explodes, suddenly there's a bright point of light that's brighter than the entire galaxy combined, and then it'll fade away over time. And what we do as a scientist, this is the most scientific thing I'm going to show today probably, is this. If you want to sound like a scientist, this is not called a graph. This is called a plot. Here where like time increases as you go from left to right over the course of about, I don't know, it's like 9 months or something, a year maybe. Brightness increases as you go from bottom to top. And this movie covers about this time span. So we can see when the supernova gets really bright, and then it fades away, and then it faded on even more. And we learned something a lot from watching this brightness change about what was going on actually, particularly with like the hydrogen atoms and the different molecules inside and around this star. All right, so let me stop there. I just want to leave you with a couple of these points again. Astronomers, we're scientists who study things in space and the universe. You do need to know math and physics, but creativity and diversity of thought are very important. We use the scientific method to discover new pieces of our universe. We can do that doing pure research or partnering with companies. And I've learned about young solar systems and explosions of dying stars, among other things. And I know most of you in this room will not become astronomers. You'll probably not become scientists. This is okay. Do what you enjoy. But I just want you to think for a second, what if you did? What might you discover? So thank you very much. I'll stop there and time for questions.
Thank you, Tom. Great talk. Questions? We have a few minutes.
How do astronomers decide on names for planets and stars without like mixing them up?
Good question. So we have a system. Basically, the stars are named according to the survey that was used to map them, or some other, based on the constellation that they're in, for example. And the planets are named in order. They go from, you start with letter B, lowercase b, and then that's the first planet discovered. And then the next planet, this is planet B, the next planet discovered is C, D, E, so on and so forth.
What got you interested in astronomy?
Yeah, so I kind of skipped that part. I was just, as a kid, I enjoyed space. I thought space was cool. I liked science fiction, wanted to go to space. Didn't happen yet. And it was just kind of one of those interests that didn't fade away. So I enjoyed science, lots of different sciences, but as I got older and older, I realized I still enjoy astronomy. I still want to learn about space. And now I'm here. You don't need a superhero origin story to be an astronomer. If you have one, that's great. But you don't need one.
Have you ever seen a planet where you think that there might be life there?
Me personally, not really, not with the work that I do. I focus on the bigger planets, which are, we think, probably less Earth-like, less likely to have life. But as astronomy in general, we definitely detected and observed planets that we think have atmospheres. So they're rocky, roughly Earth-sized. We think they have atmospheres with some sort of air. We don't know if it's oxygen or what. Maybe they have water on the surface, oceans. We don't know for sure. But we've got, I would say, some good leads on planets that could have the conditions for life. And figuring out exactly which ones do have life is a much harder problem, but one I think in your lifetimes we'll have at least some planets that we think have a good chance of having life. Now, that was very non-committal. I think life is out there, personally.
So if an astrologist were to go on the ISS, what would they be looking for, or what would they want to look for while they're on their time there, specifically?
So astronomers in space on the space station. So one advantage of being in space is you don't have the Earth's air in the way, so you don't have to worry about our atmosphere distorting your images. So you might just be able to look at the stars without having that kind of noise affecting your images. So that's one thing that astronomers might do from out in space. Yeah.
Are you gonna find aliens?
Hopefully.
Wait, have you seen an alien?
It's a good question. I mean, it's not a silly question. So the SETI Institute, where I work in Mountain View, so Mountain View right next door, is the center. It's the center for the search for extraterrestrial intelligence, aliens. It's actually pretty hard. Aliens are, who knows how far away. We don't know if they're even out there. And it's not like in most cases, not like they have a big sign up that says hey, there's aliens here. So we look for radio signals. We're always beaming radio signals out into space from our TV and radio stations. We look for those signals from other planets. Part of a program that looks for laser pulses. So if aliens, they might want to communicate between their spacecraft or their different planets in their solar system by sending laser pulses between them. We try to look for those bright laser pulses and see that as a signature that there's aliens there. Lots of different ways. It's unlikely they're just going to show up on our doorstep one day, but who knows?
So,
Yeah.
you know how we're talking about the starting out Milky Ways, and I meant not Milky Ways, but solar systems and stuff.
Yeah.
How does the rocks and the dust become planets?
Yeah, this is a really tough question. The short answer is we don't fully know. But basically the idea is you take those tiny little dust particles, and again, this is just dust. If I wipe the floor, this is the dust, right? Some of it sticks together, just you can get electrostatic charge, when you rub a balloon on your head, that can stick dust particles together. And gravity helps pull larger particles together, and then eventually they can just kind of stick and clump, and it snowballs from there. And then just slowly you go from something that's a tiny little dust speck to something that's pebble-sized, to something that's boulder-sized, to moon-sized, to planet-sized. the exact physics is still not totally clear to us, but that's the general idea. Yeah.
What happened after you discovered the disk or the planet?
So yeah, 51 Eridani b. So we discovered that planet in 2014. So really, so the first thing that happened was somebody on our team saw it in our images. They saw this tiny little speck of light. Let me just go, can I go back to it real quick? This one here. So a tiny little speck of light in our data. And they said, hey, I think this is something. We should look at it more. And someone else should kind of confirm that this is real. So we got new data, more images from other telescopes that we confirmed, okay, they also see this speck of light. It's probably really a thing, but we don't know what it is. It could be a star, it could be an asteroid, it could be a UFO. We need to get more data. So then we watched it actually over time. And as we were watching it, we watched it move. You can see that it moved a tiny bit around the star. And between that and the colors of the planet, we can actually measure the colors of these things too. We can tell from the color and its motion that this is probably really a Jupiter-like planet orbiting this star. So it took, and then we wrote a paper about it and told everybody. So I guess that's that.
Okay, I think our next speaker is also an astronomer, so
Yeah.
we will maybe take one or two quick questions before we move to the next speaker. So, yeah, go ahead right here.
Typically, do you go into your research like already knowing what you want to look for, or do you start with your data and kind of explore what you can find from that?
Yeah, you can do both. So sometimes you have an idea, you have a question that you want to answer, and you need to go get the data, right? So you say, all right, I want to look for this planet. I need a telescope that could potentially see it. I'm going to go get images with that telescope. But sometimes it works the other way around, where you just be like, I'm going to build this sweet telescope. It's going to take a bunch of images of like a bunch of things, and then I'm going to look through that and see what I find. Both work and both lead to good results.
So I had a question. How come no other country besides the United States has ever sent humans to the moon?
Oh, this feels like a political question, not an astronomy question. I mean, it's hard to send people to the moon, I guess is the short answer. I guess, yeah, it's hard and dangerous. And once somebody did it once, everyone else was like, well, why should we do it again? But I think that was short-sighted because there is a lot we can learn by actually being on the moon and studying, like, what are the rocks like? What do the stars look like from the moon? What is the moon made out of? I think we should go back, and I think somebody will soon.
All right, let's thank Tom again for his interesting talk.
Thank you.
All right, so what's going to happen is a few of your classes are going to go back to finish your class in the classroom, but some of you